Okay, welcome back to Real Analysis. We're going to continue our work in Chapter 7, looking at the notion of the derivative of a real valued function. We introduced the notion of the derivative as a limit of difference quotients in the first section, 7.2. And in this second section, 7.3, we're going to look at some of the familiar algebraic rules that you learned to compute derivatives when you were in calculus. Just like last time, here our focus won't be to present examples of these computations. So I won't be illustrating these rules. What are these rules? Well, you know them from calculus, the constant multiple rule, the sum and difference rule, the product, the quotient rule. So our purpose here isn't to illustrate how to compute derivatives using these rules. You learned how to do that in calculus. Here, our purpose is to sort of illustrate how these rules come about from the definition of derivative and, well, the algebraic properties of limits that we developed back in chapter 5. Okay, so this section actually has more rules in it than this section 7.3. So this video lecture is just for the first subsection 7.3.1. The second subsection will involve the kind of missing rule here. You probably already know what it is, the chain rule. So we're going to handle that one in a separate video lecture. This will be enough for us here. All right, so let's take a look at the statement of the main theorem. The author has this stated as theorem 7.7. It's got these 4 rules. And you should stop the video and kind of check it out, probably a little bit more carefully than what I'll say out loud here. But in each case, we have 2 functions, f and g. They're defined on some interval I, and I'm taking an element of that interval called x naught. And then everywhere, I'm assuming that both f and g are differentiable at that point, x naught. Okay. So then the paragraph goes on to kind of state what these 4 rules say. It says that although he doesn't mention it, a constant multiple or the sum or the product or the quotient, as long as g isn't 0 at x naught, the quotient f over g, they're all differentiable at x naught. And you have these differentiation formulas. Yeah. So the constant multiple rule, probably the first rule you learned in calculus for derivatives, that the derivative of a constant times a function is the constant times the derivative of that function. Constant can be any real number c. Or you learned in calculus the derivative of a sum is the sum of the derivatives. Here I'm just specifying it all at a point x naught. But of course, if these things are differentiable for every x naught in the interval, then these rules would hold for every x on the interval. Product rule, a little more complicated. It's not the derivative of the products, but rather this formula, the derivative of a product is evaluated by differentiating kind of one of the 2 functions and not the other and adding the results together. It's very familiar. And then finally, the quotient rule. Right, so the derivative of a quotient, again, under the assumption that the denominator isn't 0 at the point you're differentiating, is given by that, well, certainly most complicated expression. So you have vast experience computing with these things, right? They're sort of the bread and butter of derivative computations as you move through the calculus sequence and look at interesting applications of the derivative. So our purpose here, just to say it again, is to establish each one of these things using the definition of derivative, the limit of difference quotient, well, and together with any limit properties that are necessary to show them. It's kind of not a mystery that things like this constant multiple rule or the sum rule work this way because, well, the limits of constant multiples and limits of sums are constant multiples of the limits or sums of the limits respectively. And so since derivatives are defined in terms of limits, you kind of expect these things to be true. The quotient and product rule are a little bit more complicated, well, because the product of a sum is not the sum of the products and so on. It's a little bit more complicated than that. Okay, so let's take a look. We're going to prove 1 and 3 super carefully, citing all of our relevant limit theorems. 4, I'm going to kind of just sketch the proof because by the time we prove 1 and 3, it'll be starting to sound a little bit tedious. And then 2, I'm going to leave as one of your homework exercises in the upcoming homework set. It's going to be exercise 7.3.1. So you're going to end up handling that one. And I'm hoping what I do here for 1 and 3 gives you a good template for how you can go about constructing that proof and organizing the notation and writing it up nicely. All right, so I should have tried to leave it visible for a little bit here. So I'm gonna prove 1. So what are the hypotheses? Well, for 1, it only involves one function, so let's call it f. It's differentiable at our point x0 in the domain I, and then choose a real number. Okay, and my goal is to show that this constant function, or constant times f, c times f, is differentiable. All right, so I'm going to choose any x in the interval that's not equal to x0, and I'm going to take a look at the difference quotient. So my function that I'm trying to show is differentiable is called c times f. So I'm looking at c times f of x minus c times f of x naught. All right, so this is just the difference quotient for the function c times f. And well, by the definition of c times f of x is literally c times f of x. You have to hear the parentheses there. Same thing for c times f of x naught. And by a little bit of algebra, I can factor the c out of that thing, right? So the difference quotient that I have for the function c times f is c times the difference quotient for the function f. Let me just put some extra parentheses in to emphasize that. The difference quotient for the function c times f is c times the difference quotient for the function f. Okay? But now I can use limit laws. In particular, the limit law that I'm using is about multiples of limits. It's theorem 5.15. Yeah, that law says that the limit of a constant multiple times a function is that constant multiple times the limit of the function, if the limit exists. Well, I know that the limit of this difference quotient over here for f exists because f is differentiable. I'm assuming f is differentiable. So if I take the limit of both sides of this thing, on the left-hand side, I'm just plopping that in down here. The limit of the difference quotient for c times f, by that rule, is c times the limit of the difference quotient for f, but that limit exists and equals f prime of x naught because f is differentiable. All right, so what does that computation show? It shows that when I take the limit of the difference quotient of the function c times f, I get a real number, and that real number is c times f prime of x naught. So it precisely shows that cf is differentiable, and the value of its derivative at x naught is c times f prime of x naught, right? So maybe you should pause there and kind of let that sink in, but I tried to write it out in sufficient detail that shows exactly how I'm using that theorem 5.15 and the definition of derivative. Okay, it follows directly from those two statements, those two facts, two ideas. Nice. Okay, so like I say, I'm going to leave 2 to you. Let's take a look at, sorry, this is the proof of 3, not 2. Let me just addend this here. This is the product rule. So the product rule involves two functions, f and g. So let's name them that. They're both differentiable at this x naught, and let's pick an x that's not x naught. And again, I'm going to just start by algebraically investigating the difference quotient for the function f times g. Okay, the difference quotient for the function f times g is f times g of x minus f times g of x naught, all divided by x minus x naught. Well, f times g of x is by definition f of x times g of x. Okay, and likewise at x naught, it's f of x naught times g of x naught. And we've seen this idea before when we were proving things about limits of products. I'm going to kind of strategically add and subtract a term here. I'm going to subtract g times g of x naught times f of x, but I'm going to add that term back. Okay, so if you want me to kind of color code here, f times g of x is equal to this term in my numerator over here. F times g of x naught is the last term in my numerator over there. It's got a minus sign in front of it. And the two green terms are equal with opposite signs, and so their sum is 0. So that's what justifies this equality. Okay, and then just a little bit of algebra. Out of the first two terms over here, I factor out an f of x. Out of the last two terms, I factor out a g of x naught. It's just that I'm factoring that f of x out on the left and g of x naught on the right, but that certainly doesn't matter because the order of multiplication is irrelevant. What's left? Well, the difference quotient for g times f of x, the difference quotient for f times g of x naught. All right? So I'm almost ready to take the limit of both sides of that equality. And by that equality, I mean I'm looking at the far left-hand side and this sort of simplified version of the right-hand side. But one comment before I do it, I need to remember that a differentiable function is continuous. That's what we proved in the previous video lecture. So 7.6 says that if f is differentiable at x naught, then it's continuous at x naught. So when we go to take this limit, this term that I'm going to just kind of underline in blue, the limit of f of x as x goes to x naught is going to become f of x naught. That's by continuity, right? So the limit exists and equals the function value. G and f are differentiable. So these difference quotients both have limits that exist. They equal g prime of x and f prime of x respectively. So that's what I'm writing down here, right? So this difference quotient up here, g of x minus g of x naught over x minus x naught, that's going to approach g prime of x naught by definition. G is differentiable at x naught. Same thing for the f difference quotient. Okay, so what am I saying? I'm just looking at the pieces over here. I've got a sum of two products, and each factor in the product has a limit. This is actually a constant. So you can think of that constant as having a limit, or you can think of it as a constant multiple. I mean, it's a constant in the sense it doesn't depend on x. It's g of x naught. And we have limit laws. I looked up their numbers. I'm using 3 of them. I'm using the fact that constant times limits pull out. The limit of sum is the sum of the limits. The limit of a product is the product of the limits. So if I roll all of that together, I tried to write this out explicitly. If I look at the limit as x goes to x naught of the difference quotient for f times g, well, I'm going to plop in that expression that we just had up there. Okay. And then I'm just going to push through using these limit laws. That's the limit as x goes to x0 of f of x times the limit as x goes to x0 of the difference quotient for g plus difference quotient for f's limit. G of x naught's a constant, so it just stays out there. It comes through the limit. Okay, but like I said above, f is continuous. So this limit, I don't remember what color I was using. I think it was blue. That limit is equal to f prime of x naught. These two difference quotients, respectively, have limits f prime or g prime and f prime. G of x naught is just the constant sitting there. So that limit exists. So that means that fg is differentiable at x naught. The limit of its difference quotient exists. And in fact, we get this formula. Its derivative's value, fg prime at x naught, is, well, this formula that's written above. It's exactly the product rule. Nice. Okay, so again, I would kind of stop and kind of parse through that at your own pace. Make sure you understand when and where I'm applying these limit laws and how I symbolically wrote it down. But I tried to give you a good roadmap for it. The quotient rule, I'm going to be a little bit more brief. So I've kind of tried to lay out the ideas here, and I don't want the video to become too tedious and my tongue will start tripping on me. So to prove the quotient rule, I'm just going to kind of bullet point out the main ideas here. All right. So what are these bullet points? Well, one of them is that if g is differentiable, then it's continuous. Okay, so g is a differentiable function at x naught, it's continuous at x naught. That's our theorem 7.6. We use that fact in the product rule as well. Second bullet point, g of x naught isn't 0. So if you have a continuous function and it's non-zero at some point, then it's non-zero in a neighborhood of that point. Okay, so there's some neighborhood, some epsilon that's greater than 0, that the function g isn't 0 for every x in the neighborhood around it. Right? A continuous function that's not 0 somewhere is not 0 in a neighborhood of that point. It'll be used below. So I'm going to do some algebra. As long as I stick to that place where g is not 0 and I take x's that aren't 0, what I'm worrying about is I don't want to think that I'm dividing by 0. So g of x isn't 0, g of x naught's not 0, x minus x naught's not 0. So all of that fussing was to make sure that nowhere am I writing something in a denominator that could possibly equal 0. All right, and then maybe I just won't even narrate this. I'll let you do the algebra. What did I do? I took a difference of those fractions. I got a common denominator, rewrote that thing. I'm doing something similar to what I did above, where I'm subtracting and adding a certain term in the numerator. Okay, so that algebraically is equivalent. Then I'm just rewriting this thing, bringing out the 1 over the product of the g's. writing this thing as, something times a difference quotient. If you look carefully here, you might notice that I've got a g of x0 with a plus sign and a g of x with a minus sign, and I switched the order of them here. Well, that's what that minus sign is doing. So stop the video and just check my algebra. I tried to double check it before I started this video, so I think it's all correct. And then I would take the limit as x goes to x0 of both sides of that equation. Right, so I'm not writing it out as much detail here, but what would happen? Well, the g of x is going to approach g of x0 by continuity. So I'm going to get 1 over g of x0 squared out there. This thing's a constant. The difference quotient for f is going to approach the derivative of f at x0. Push the limit through the difference. F of x0 is a constant. The difference quotient for g is going to approach g's derivative, and there you go. There's your quotient rule formula. I've got g times f prime minus f times g prime all over g squared, right? So there's the proof or sketch of proof of the quotient rule. Maybe a good exercise would be for you to sort of write it out in as much detail as I did the product rule, citing by number the limit laws that I'm using in this last step. Okay, so it's sort of a nice way for you to explicate that proof. Make sure you're following along. Okay, so I'm going to keep this a little bit on the short side, but I just wanted to kind of end by suggesting some things that you might want to practice by induction. We haven't had many induction arguments, at least globally. I mean, as a group, come up in our class recently, and it's a skill that you want to keep sharp. So here are some sort of slight generalizations of at least a couple of those rules above that you would prove using induction on the number n. So everywhere below here, n is a natural number. I didn't keep repeating it. So I've just stated these things as some corollaries. The first one is that if you take a bunch of functions, n of them, on I, and they're all differentiable at this point x naught, well, then their sum is differentiable at x naught, and the derivative of the sum is the sum of the derivatives. All right, so the exercise that you're going to do from this theorem, the second part of it in your homework, is the case where n is equal to 2. So you could use that as your base step if you want. And then proceed with an induction argument to show that it's true if you're summing any number of differentiable functions together. Nice. I'm not going to do it, but yeah, I hope you will. Second corollary for products. If you take n functions that are all differentiable at x naught, the product of them, f1 times f2 and so on, is differentiable at x naught. And the product formula, I think it's actually a little bit more interesting than the sum formula. The derivative of this n factored product is, can you kind of see the pattern? You differentiate one of the factors, multiplying it by the rest of them undifferentiated, and you just have to move that factor through. So on the first line that I didn't write here, it would be like f1, f2, f3 prime, f4, all the way to fn. So the prime is just sort of slowly migrating one factor at a time across the entire thing. So there's n terms in this sum. There's n terms in the sum. I can write that here if it's helpful for you. This is sometimes referred to as the generalized product rule. The product rule is sometimes also called the Leibniz rule, the generalized Leibniz rule. Very fun induction proof. You should do it. And then the last corollary of it is just kind of a special case where those n functions are all the same. So if you take a differentiable function, and let's write by f to the n, I just mean the product of f with itself n times. So this n, it doesn't represent n-fold composition. It means n-fold pointwise product. Okay, so if f is differentiable, so is f to the n. And the derivative of f to the n will be n times f to the n minus 1 times f prime, all evaluated at x naught. Okay, and this is a kind of a nice place to end, because this kind of reminds me of another rule that we're going to speak about in the next video lecture called the chain rule. But I want to note here that I didn't use the chain rule. So the proof of this corollary 3 that I have in mind does not need the chain rule. Once we have the chain rule, we could certainly prove it with that, but you can derive this from corollary 2. Okay, so thanks for listening.